All right, this video is to take you through an introduction to circular motion. The top of the screencast says AP Physics C, but this is the same video for P1. That you guys have the same first 2 pages of your notes at least. So starting off just with a review of when we look at acceleration. So if you remember from our kinematics unit, we talked about this idea of the total linear acceleration of an object being a vector sum of the parallel component plus the perpendicular component of acceleration. So this parallel component here, we associate that with the change in speed, and the perpendicular component was associated with this change in direction. So essentially, if we have some velocity vector that is moving this way, the parallel component of the acceleration would be kind of either with the velocity to cause a speeding up, or against that velocity to call a 180-degree opposite from that velocity, and that would cause the slowing down. And in any kind of acceleration that's associated that is perpendicular to that velocity, this acceleration would only be associated with a change in direction. So again, these accelerations would also be associated with some net force, because we're kind of very familiar with the fact that the net force is proportional in magnitude and direction to the acceleration. So let's look at first at examples of what we call non-uniform circular motion, which encompasses both of this slowing down as well as changing direction. So as a quick example here, let's pretend we have like a roller coaster car that's chugging along, and it hits this loop-de-loop, and it's going to move around, go upside down in a circle, just like a roller coaster ride. So if we look at positions at point P and point Q, we have a couple of forces that we can associate with the acceleration. We have a normal force acting downward, has the track pushing down on the car, and then of course we'd have the force of gravity acting on it. So if my car is moving in that direction as it's doing its loop-de-loop, we see at point P, we only can associate these forces with a perpendicular component of the acceleration, because it is only acting, there's no component of that force that acts either with the velocity vector or against it to cause it to speed up or slow down. So at that moment in time, we're just looking at a change in direction. Now we go to position Q, then we have this force of gravity that is acting downward, and at the same time, we have a velocity vector that is also going downward. We see this is associated with what we would call a parallel, and that force of gravity would be causing that speeding up of that velocity vector. And then any place along in the middle, you would have a combination of both the parallel and perpendicular components. And we'll certainly discuss that as we kind of move through non-uniform circular motion. Now, circular motion, or uniform circular motion, which will be the focus of the front part of this unit, is constant speed. So your A parallel would be equal to 0, and we're really just looking at this perpendicular component where we're looking at that change in direction while it's moving in a circle. All right, so a few definitions before you guys can get into the lab and do the sim activity. The period, which we use a capital letter T to signify that. That period is the time for one cycle or one revolution. And we use SI units to measure that, and that would be in seconds. Frequency, we use the same letter that we use for the force of friction. So this is context clues. You have to kind of look at the problem to realize is F for frequency or F for friction. But frequency is the number of cycles per second. So how frequently something rotates. Cycles or rotations or revolutions, any of those words per second. And the SI unit is inverse seconds, or sometimes you'll see it written as hertz, which is abbreviated HZ. So that is an inverse second. And then average speed, and we're talking about linear speed here. We're going to talk about rotational speed in a minute. That is basically the change in position over change in time. So this is, again, for objects moving in a circle. Objects moving in a circle. The distance that the object is going to travel is going to be equal to 1 circumference of that circle, circumference, divided by the time it takes to do one trip around, and that would be the period. And then if we remember the physics equation, or the math equation for circumference, you would take 2 pi times the radius of that circle divided by the period. So this is going to be a very useful equation that we will use in the lab. Okay. And I probably should have mentioned this before, there's kind of an obvious relationship here that maybe you can see from the units. That period is equal to 1 over the frequency. So there's this inverse relationship of those two things. All right, so a little bit about rotational motion and kind of looking at the analog or the equivalent from the linear world to the rotational world. So we've all spent some time talking about position. It's measured in meters. But in the angular world, we'll use theta to indicate an angular position. The unit for that is radians. And kind of the equation, and what I mean by the equation is how do we get from the linear to the angular world, is the arc length equation that you might remember from a geometry class. So S represents a linear distance, an arc length, and if we look at very small thetas, we can kind of approximate that to be just, you know, a straight line or something. But this linear distance here is an arc length. And then R is the radius of the circle, and theta is measured in radians. So 1 radian is equal to 57 degrees. We won't really be putting our calculators into radians much at all in this unit, although we do mention radians a lot. So a radian is a dimensionless unit. So it's kind of like a placeholder. Dimensionless, yeah, I can spell. Here, so if what I mean by a placeholder unit, so if we measure this linear distance in meters, and R is measured in meters as well, and theta is measured in radians, we would not express a linear distance as a meter radian. This radian, once you multiply by something, just kind of goes away. So that gives you the idea between how do we get from the linear to the angular world. So S is equal to R theta. All right, moving on to the next page. Average velocity, of course, is the change in position over the change in time. It's measured in meters per second. The rotational analog is a lowercase omega. So getting your Greek letters on here, it's kind of like a curly looking W. I put the bar over here to kind of indicate that it's an average. And this has the same kind of rotational analog here. Instead of change in linear position, it's change in angular position, change in theta over change in time. And the units would be radians per second. Instantaneous velocity, we've studied before. That is the slope of the tangent line. Kind of getting back to our graph, so a position versus time graph. Instantaneous angular velocity would just be the omega, and again, vector quantity, and this would be the slope of the tangent of the angular position versus time graph. So again, a lot of rotational analogs, there's nothing really different, just the letters get a little bit different, the units are a little bit different, and we just have to be kind of making sure we're understanding that context. All right, instantaneous velocity. So now that we're kind of putting in some things, we'll kind of summarize some of these formulas. So we know that the linear velocity is going to be equal to 2 pi over t here. Angular velocity is change in position over change in time. So the total distance it would travel is 2 pi radians in one period. So kind of the relationship between v and omega. If we kind of put these two together, we see that v is equal to r omega. So we can see some patterns here. The linear speed is r times omega. The linear distance is r times the angular position. So there's some definite patterns here that we can see. But what do you get on your equation sheet, which is most important? As it's written on your equation sheet, it's written this way. So t, or period, is equal to 2 pi divided by the angular velocity, and that's equal to 1 over frequency, which kind of encompasses everything that we've mentioned today in one line, just a little bit differently, but this is what you get on the equation sheet. Okay, some unit conversions that might come up. Just as a reminder, there are 2 pi radians is equal to 1 revolution or 1 rotation, and that's of course equal to 360 degrees. So if asked to do any kind of dimensional analysis, we do need to kind of remember how to convert these things. All right, so just a couple of try it questions. So I'd like you guys to just pause the video and try these 4 questions. See if you can get them, and then come back to the video and check your answers. All right, so coming back to it, the linear velocity of an object, I'm asking for v. I have the radius of 3 meters, and the time of revolution is the period. So v is equal to 2 pi r over t. Plugging in numbers, I get 2 pi times 3 meters over 0.25 seconds. and this is going to be 24 pi meters per second. Students often ask, can I put my answer in terms of pi? Well, sometimes you see that as a choice on a multiple choice thing. I'm not a huge fan of it, but it's okay. I'll certainly have both. But if you do multiply it out by pi, it would be 75.4 meters per second. So do not forget units. This is the unit, this part of AP Physics where they really get particular about you including units on numbers. So make sure you get the units. They're usually worth some points. Okay, the angular velocity is asking for the omega in radians per second. So that relationship, if we remember, V is equal to R omega. So omega is equal to V divided by R. So I can take the 24 pi divided by a quarter second, and that'll give me 8 pi radians per second, which is equal to 25.1 radians per second. Okay, converting that into revolutions per second, 8 pi radians per second. So 2 pi radians is equal to 1 revolution. So the radians will cancel out, and we get 4 revolutions per second. So just checking through some of the work, some basic calculations here. Determine the speed of the object that's moving at 0.6 meters per second in a 0.3 meter radius circle. This is a linear speed. Looking at the units, I can tell that it's not an angular speed. And then I have the radius. So the period, I'm asking for big T. So V equals to 2 pi R over T. I can substitute numbers in and get 0.6 is equal to 2 pi times 0.3 divided by T. And I can solve through and I get pi seconds, or if you want to be real, more decimal places, 3.1 seconds. All right, so this is just, hopefully those problems were not too challenging, just some basic stuff. And I just wanted to get you kind of introduced to what you'll be doing with the circular motion lab that is coming up next. You will be measuring period and calculating linear velocity of a object that is moving at constant speed in a circle.